Okay, I guess we get started. Well, good afternoon. Today, Maria Klepikova from CNRS is going to be giving a talk here on the impacts of anthropogenic forcing on subsurface thermal means. So, without further ado.
Thank you very much. So, good afternoon. First of all, I'd like to try to position my subject relative to the lectures of this morning. There was one of last questions coming from this side to Peter Bayer regarding the importance of advective forces versus conductive forces. And as Peter said, when we are staying at the scale of several kilometers, let's say catchment scale, and when there are some groundwater flow, which is often the case, these studies where we take into account these conceptual models, where we take into account only conduction, they can fail. And basically this is where my topic comes on. So I will talk about the influence of hydrodynamic on, on thermal regimes of the subsurface. I think I have no battery anymore. I can talk without the support also, but oh. No, it's not this. Perfect. But I still prefer to. So. So currently, very often we believe that the thermal regime of groundwater system is stable. And we believe in many studies that temperature of groundwater is regulated by the heat flux, geothermal heat flux coming from the depths, and long-term surface, the temperature of the ground surface. And this presumed thermal stability is critical to drive many processes in the critical zone that was introduced by Danny previously. Because first of all, it drives rates of biogeochemical reactions, so it controls biogeochemical processes that allows us to have, for example, clean drinking water. And also it allows groundwater to buffer temperature in streams, and so to control the functioning, the normal functioning of aquatic ecosystems, like fish and some smaller species. On another side, we also know that currently, as Peter presented this morning, we have many relatively new forcings. We have, first of all, climate warming, so atmosphere warming. We have also all these changes in the occupation of ground surface, urban heat islands. We also can have deforestation that globally rise the temperature of the surface. And we also have basically abstraction of groundwater, which is happening all around the globe. And we also know that globally all these factors, they rise the temperature of surface water, and in most cases, unfortunately, they have a negative impact on ecohydrology. So if you have warmer water, we will have more microbes, more contamination, so less drinking water, and we also have less biodiversity in warmer water. Not always, but very often. The question here is that it is logic that groundwater should follow all this warming of the surface, but there is some delay that is not very well quantified, and also we don't really know the amplitude of these temperature changes in the groundwater. So from one side, it's logic that as ground surface is warming, we should have groundwater that is warming with time, and on another side, we know that we have intensification of groundwater flow. And this intensification of groundwater flow in terms of temperature, it could mean that as we have the decrease of permeability with depth, which is known since long time ago, it seems that we accelerate groundwater in the shallow subsurface, which is colder, and there is less flow in the deeper subsurface, which is warmer. So it could be that with time, this acceleration of groundwater flow due to abstraction will imply that groundwater will cool down. At least there are some studies in nature that shows this at large scale. another problem is that we don't really have not so much data that could allow us to say which process is most important, warming or cooling down, because we need temperature profiles since many decades and this data are rare. And in terms of modeling, the conceptual model of such a systems at smaller scale, it's not always easy to say how they should look like. It is known that temperature is perturbed by groundwater flow at the scale of the catchment. We have infiltration of cold water in a recharge zone, so we have cooling down from the surface. We have upwell flow in the recharge zone and in discharge zone, so we have upward flow of relatively warm water, but in the reality we often have heterogeneity in hydraulic properties of the subsurface. Could be fractures or just some heterogeneous fault zones or whatever. And we know that it will also perturb somehow the temperature at the scale. We can predict this kind of perturbation at the scale of the single fracture. This is the result that is related also to Chinhua presentation this morning. So we know that fracture provides fast transfer of temperature, of energy, and we can predict how it works, even at the scale of simple fracture networks. But we don't really know how to take out this heterogeneity at the larger scale and how we can deal with all these millions of fractures that are present at the scale of the catchment. So I will just try to show you some data that shows that indeed temperature changes and some insights how we can deal with conceptual models at this scale where the hydrodynamics takes an important role. This is one of the examples. It's not my study. It's by Benz and Barrett, by Victor and Barrett, sorry. So this is the data, one of these rare data, I would say, where they were able to measure temperature profiles, repetitive temperature profiles, over decades in Netherlands. So what you can see here, we have depths, 300 meters temperature from 8 to 16, the same x-axis on the right and on the left, while on the left we have temperature measured at 80s, and on the right we have more or less the same boreholes measured in 2016. Colors mean that we are staying in the different areas in terms of occupation of ground surface. Green means forest, blue means agricultural zone, and red means urban area. So first of all, you can see that we have globally changes of temperature. So temperature changed since 35 years. It went, so it warms up, certainly. We can also see that indeed the warming signal comes from the surface, which is logic. But what we can also see that the depth of propagation of this warm signal from the surface is not the same for different profiles. In terms of surface occupation, we can say that logically forest area is not so heated up, agricultural area is not heated so much, and in urban islands we have the most important warming, which is logic compared to what Peter presented us this morning. But what I want to say is that normally, according to Fourier law that Peter presented, we should expect that like inflation point, which so this is the point where the thermal gradient is 0, should be situated around 20-30 meters depth. And this would what we expect if there would be only conduction presented as a main heat transfer process in this area. But we see that at some areas this inflation point is situated at around 100 meters, 80-100 meters. It means that there is some additional heat transfer process, and this is an advection. So we have vertical flow, most probably downward, that impact these temperature profiles. So there is an interaction of climate change and hydrodynamic, at least on this side. But for this case that I have shown right now, it was a natural groundwater flow. And as I said, sometimes, very often, at the scale of the globe, we abstract groundwater, so we change groundwater flow. And this is where I want to come. What would happen if we would pump in a perfect porous aquifer somewhere? We have, without the pumping, we would have the geothermal gradient, like here, like the black line. And then we place an abstraction point at some depth. And water, if we don't have any heterogeneity that blocks the flow, would come from the surface and from the down towards the pump. It would also transport the heat with this water. It means that we would have like a negative temperature anomaly above the pump and positive temperature anomaly below the pump. And at the end, we observe this kind of S-shaped temperature profile. If we now have a fractured aquifer, this is a little bit different, because in fractured aquifer, flow is mainly happening in faults, in fractures, and there is nothing flowing through the matrix or just a little bit and not perturbing temperature too much. Imagine that we have a fracture, which is almost vertical one, but it could also be another direction, a horizontal one. In this case, if we pump in here, we would bring the water from the higher depths with a high velocity, and it would give us, in this case, positive temperature anomaly, but depending on orientation, it could be also not so strong anomaly or even negative anomaly. But always, if we pump, we try to have an aquifer, which is often it is situated deep in there, and so always we bring hot water from the depths, often. So this is the conceptual model that we try to check versus some data that we would have that we try to find in different hydrogeological configurations. And so the first study case that we wanted to investigate, this is the site in Netherlands. It's called La Cabine, French name. This is an abstraction site in unconsolidated sediments, pretty homogeneous, more or less the same properties, hydraulic properties all over the different aquifers, and they pump at some depths since 50s at a rate of 10 million cubic meter per year. And this is like a drinking water for this Veluwe area in Netherlands. Another case study that I want to show you is a famous Plumer aquifer in France. Some of you have traveled there, have worked there, and if not, you are welcome to come. So it's like 2 hours driving from Rennes, and this is a granitic field site where we have a lot of fault zones, and most of them are almost vertical. And so normally granite is not so permeable rock, but as we have this fracture zone which are very well open and of very high transmissivity, since 91 this site is used as a pumping site for the drinking water for the small city of 20,000 inhabitants, and so they pump at 1 million cubic meter per year, so since 33 years then. And we also have some research site close to this pumping station that allows us to investigate what is the effect of pumping on the groundwater, on biochemistry, on temperature, on whatever. And we can also have a smaller site close to it where we have a huge amount of experiments like fiber optic withdrawn, etc. So now let's see what the temperature measurements gives us at these two completely different locations. So this is just what we observe at the surface. So we have a meteor station that allows us to say what is the climate warming at these two areas. So basically since 75 the temperature rise at both sides by 1.5 degrees more or less. It's a little bit colder in Netherlands than in France in this case. And then we have temperature data. So in Netherlands, they not have very old data. They just started to observe temperature in 2016, and then they repeated temperature profiles several times. Last year. So they pump at the depths of around 90 meters, and as you can see, indeed, we have this S-shaped profile, which stops at 180 meters. Then we observe just a geothermal gradient, but here this geothermal gradient is certainly perturbed by the pumping interval that is situated in here. And we can also see a little bit that it's warming at the surface. Then basically this warm signal is propagating downward towards the pump, and here we have just the warm water coming up because of the pumping. So this is what we see. Now, example from Plumeur side. So we pump from the fault zone. As I said, it's almost vertical. This is we know because we have a lot of different investigations in there. And what we can see, so we started to measure, not me, but before, it was before me, at 96. And then we have a profiles from 2005, 2020. So what we can see that, so the first profile, it's already 5 years after we started to pump. So it's already not just the geothermal gradient, but already perturbed since 5 years of pumping. And basically, so starting from the depth of 40 meters, we have this huge temperature anomaly, which is around 3 degrees. And as you can see, so we even measured last year, so it's still heating up slightly. So even after 35 years of pumping, we are still not at steady state region. We continue to heat the subsurface. And we heat the subsurface, so at 100 meter depths, we are still 300 degrees higher than it would be under the natural conditions. There also we have a huge amount of profiles, so we observe similar temperature patterns in all the boreholes in 1 kilometer around the pumping station. And once we are more far away, so at the distance more than 1 kilometer, we still observe some heating signal, so warming signal, but not so strong one. So most probably it's just the heat propagating by diffusion furthermore. What is important to say here is just the comparison. So at the same time scale, we heat up the surface by 1.5 degrees from the global warming, but because we pump, we also heat the subsurface, and this is like at least 2 times more since 30 years. So it changes temperature a lot. We have very simple model, very simple conceptual 2D model, which is easy to run. To try to reproduce this kind of data with knowledge that we have about the field sites. So here we just have a homogeneous porous aquifer with more or less the same hydraulic properties. We start to extract water in there with 10 cubic millions, with 10 millions cubic meter per year. We have some recharge at the surface, and basically we more or less capable of reproduce similar shapes of temperature profiles. And the same for fractured aquifers. We just induce the fracture in here, fault zone. We start to pump from the fault zone. We bring hot water in here, and we observe more or less similar profiles, but they're not perfect. So they're not starting to stabilize with time. So it's kind of could explain more or less what is happening, but not exactly. But it is hard to try to constrain this model better, because we are starting to add new complexity, and while we add new complexity, we need more and more data. The model is more and more heavy, and so we need a huge amount of data, and we also need a huge amount of parameters in the model, so it's hard to turn it. So the question here, what kind of models should we also use in future in order to predict this kind of configuration, especially in fractured media?
Maria,
yes. Yes.
Here.
Sorry.
So you measure in the same borehole that you pump, or is it separate?
No. It's kind of 50 meters away from the pumping well. But it's interesting because, like the technician that are working there, the temperature is not the parameter that they supposed to measure with time. They just measure some basic chemistry parameters. But the guy who is just measuring with a simple sound, he said, "Oh, it's interesting that you are measuring temperature, because I just even feel that the water is super warm since 20 years when I'm working here." And he said that it's also a problem in many stations that where he measuring chemistry. But nobody's really tried to measure this in terms of community administration, etc. So this is all about the pumping. And now just another example of how we perturb natural groundwater system with some constructions and anthropogenic forcings. So now we are going to Mont Blanc tunnel. So this is the 12-kilometer tunnel in between France and Italy, just below the Mont Blanc. And we have a French-Italy border somewhere like 8 kilometers far away from the France side. And this tunnel was constructed in 59, 58. And unfortunately, in '99, there was a big fire that killed like 40 persons in there. And since then, so they never really closed, I believe, the tunnel completely, but they are always trying to increase the security, to add new stuff, to be sure that there is no fire anymore. And for us, it's good somehow because sometimes they close the tunnel completely and they allow the researchers to come in and for free to get a huge amount of data if you want, so you can also go there. So this is just the picture that is coming from the paper of Jean-Christophe Maréchal in '99, by the way, the same year when it was the fire there. So he was measuring, so the inflow, basically when you drill the tunnel in the mountains, you always have inflow that is coming because you perturb the system and you connect fractures and fault zones that had a big pressure inside to the atmosphere, and water starts to overflow, to inflow to the tunnel. So when it's drilled, these inflows, they're pretty huge. So in one of the fault zone, which is coming from the glacier, of course, there was like 1,000 liters per second coming in. And then with time, the system stabilizes and this flow goes down. But unfortunately, nobody really measures these inflows because it's just the road in between France and Italy. It's very hard to manage the systematic, maintain systematic measurements in there. And so these are the flow rates that were measured when the construction was, when it was constructed. And what is interesting for us is that these fractures and flow zones that connect the tunnel with the surface, with the glacier in this case, they have a very contrast temperature. So this is the picture that I took with an infrared camera. You can see that in general the walls are at this part at least at 22 degrees, but we have inflow zones here, here and here that are at 8-10 degrees. Even with infrared camera it's very visible. So they are pretty thin, only a few centimeters, but they are very cold and they bring these negative temperature anomalies. We can also go on this road because there is no car and just sample the groundwater and measure the temperature with the temperature transducers. So it was done during the construction. Of course, it's again we have noise because it's not the same temperature sensors, etc. Then in '96 by Jean-Christophe Maréchal, we have all these pink points, and finally this year, this winter, we measured these black points. So what we can see is that this general pattern, so this is the French entry, Italian entry, 12 kilometers in here. So we have this general pattern like this. This is just because we have the topography of the mountain. Then we have all this kind of noise, and this is just because we have all these fractures, fault zones, that bring cold water from the surface. And of course we have this huge negative temperature anomaly, which is coming from this fault zone. What we can see that in general the temperature goes down since the construction of the tunnel. And why it's interesting for us, so I didn't analyze this data yet, because first we can use this transient temperature anomaly in order to constrain the geometry and the hydrogeological properties of the fault zones. This is interesting because these fault zones, they are not very well characterized. Of course there is no boreholes in there. And apparently some guys from ETH, they have seen that there is also seismicity since several years below the Mont Blanc. And also the question that I don't know the answer, so what is the interaction of this groundwater flow that is coming from the glacier with the glacier itself? Because so we take some cold water from the glacier, we cool down the rocks, so we take some energy, and it's not really evident for me how it, so maybe it's even allows to warm up the glacier, I don't know. So this is something that we would need to investigate, but we need much more complex models because glacier it's difficult to take into account. What we are going to do in future is just example for at least some of you who knows DFN Lab now. So very performant tool that exists is DFN model, so discrete fracture network models. But all of these models now, they're taking into account only fractures. So we can model flow, pressure, and transport in this kind of fractures, but matrix is never discretized. And what we are doing, what Benoit is doing, to be honest, is he is trying to include the matrix And so this will allow us to consider both advection through the fractures and then diffusion to the matrix, and it will be new kind of models. This task was already solved partially by Silvia, which should be here somewhere, I think. Yes. So the one, so it's very good study, but it was solved only for the short distance, short distance of diffusion towards the matrix. So it worked for some, I would say, geothermal investigations at short time period. But if we want to investigate this kind of systems for decades, etc., we would need to expand this solution and include more matrix in this model. So the next step would be to run a lot of different synthetic configuration and try to find out what is the relationship between the structure, organization of the fracture network and the heat transport, and propose some effective models for this kind of systems at the scale of big fracture networks at the catchment scale. Just some take-home messages. So first of all, at some scales and where we have groundwater flow, we should consider the coupling of hydrodynamics and climate change to estimate the evolution of the temperature of groundwater systems. We also don't have too many data which allows us to analyze the distribution of temperature in the surface, because we need repeated temperature profiles for decades, and the data that we have should be analyzed with a new kind of tools that we are trying to develop. And certainly that the exploitation of groundwater system, it changes a lot the subsurface thermal regime, and sometimes this impact is even more important than the impact of climate change. And this is just the list of the people who participated in these pictures. Yeah, thank you.
It's not clear to me why pumping is raising the temperature of the groundwater. Is it because it's before that inflection point?
Because we have geothermal gradient. So at the surface of groundwater is more or less, so on average it's 12 degrees. When you are going deeper, the temperature increases on average 3 degrees per 100 meters. You are starting to pump, you bring groundwater from the depths, because you don't have groundwater on the surface, so you bring deep groundwater, it's warm.
But is that still happening in aquifers that are affected by this overnight island effect?
What do you mean?
Well, people pumping from that deep.
It depends on site. So if you are in a porous aquifer, you are pumping maybe not from so deep because you are pumping from everywhere. But when you are in fractured aquifer like Plumer, but there are many other cases, of course, you are connected to the subsurface, to some sources of groundwater that are deeper. So very often you bring some hot water from the depths with pretty high velocity, at least not with a natural velocity. So you perturb the system. Yeah.
Following up, so where do you bring this hot water from? Because you're pumping them out, no? You're removing them from the system. And actually, I was thinking that the water level.
There is also changes in water level. Of course, this is there are a lot of studies about the water level.
So actually, all the water should go even further down, no? Like regional decrease as you are removing a lot of water from the.
But this is another topic that we disconnect also the rivers, and we modify the organization of groundwater. This is another topic. But just the fact that we bring hot water. So, for example, in Plumer, knowing that since 30 years we rise the temperature by more than 3 degrees, this water should come at least from 700-800 meter depths. So this is what we can roughly estimate from the geothermal gradient and from the velocity that we could expect for this kind.
You bring water from down, you don't bring them and mix them to the ground, you know? You remove them out.
So yeah, we remove this out, of course, yeah. We drink it.
Exactly.
Yeah.
How do they warm the groundwater? I don't see.
Flows.
By flow? I don't understand.
Maybe I'm missing the mechanism. I mean, if you ever, I'm not a hydrogeologist, but if you pump a well and you remove the water.
Yeah.
But the water's coming from way deep below. The water's coming up to the point you're pumping, not coming down to the point you're pumping. So you're pulling water from below into the pump. Right?
Yes?
After the screening, okay. I see. You're mixing it before you do it.
Yeah. Okay.
One more question.
Yeah.
With fractured aquifer, is it mostly from the deeper part? Can it be also equally likely that you could bring in from the shallower parts through vertical fracture down deep?
I'm not hydrogeologist neither, but in my opinion, if you have some fracture which brings you water from the surface, then it will not be very productive aquifer because you will empty the lake from which you pump, and that's all, no? I don't know, maybe it exists in the nature. Some hydrogeologists should tell us this, but...
Just to following up on that, so are you saying that most of the temperature profile that you see shows a signature of water coming from down? You don't see the signature?
So on what I have seen, it's always warm water. But of course, it's under some configuration, you should have maybe almost horizontal fractures. In this case, you will not bring some deeper or shallower water, and so you will not see this effect. But we should have data. Yeah.
I think at this site also the thing is that the boreholes are drilled up to a special places, which is a fault zone that's vertical, and that is actually places where flows are naturally upwards. So that's why when you actually pump there, you kind of increase these flows that are going upwards.
Yeah, that makes sense. But there could be a downwelling flow zone too in fractured aquifer.
Yeah.
It could be, yes.
Could be.
But in all this area, what we observe is always positive anomalies. Yeah.
Can I ask
Yeah, sure.
I don't want to fill the student, but in the hypothesis that as the surface warms up, we get warmer water.
Yes.
entering. Are you considering the seasons where water is entering into the subsurface?
That what water that...
Are you considering the seasonal effect that could be
Yes.
10 or 20 degrees?
But the seasonal effect should disappear at 10-meter depths, but of course it could...
No, the seasonal effect of the recharge, of course it exchanges heat, but if the assumption is that the air temperature,
Yeah.
average air temperature will be warmer,
Yeah.
and therefore the water will be warmer,
Yeah.
that's true, but not if the season when the water is happening is cooler or it's snow melting.
Yeah, but I mean, right now it's just the average recharge, so we are not considering every year, etc. But of course, it could also have some effects on this.
Okay.